Alright, so here we are with what we're going to be doing, which is the 3-4 assignment, but we also want to fill in the reasons packet from the 3-4 notes as well, so that we have that to reference. So if we go forward in the notes packet, again, these should be filled in, unlike mine. We're going to number 23, which has the perpendicular transversal theorem. And so in your notes, that was the one that was 3-4-2. It had an actual name to it. And so we'll just go ahead and get the idea here. So officially, the definition was, in a plane, if a transversal is perpendicular to one of two parallel lines, that it is perpendicular to the other line. So we're going to say if a transversal is, where are we, perpendicular to one of two parallel lines, then it's perpendicular to the other line. And I'm just going to say to both. So again, the idea here is that we have this first piece where we have two parallel lines, and the fact that the transversal meets one of the parallel lines at 90 degrees. So again, we're given those are parallel. The second piece would be that we would have the two parallel lines and the fact that the transversal is perpendicular to both. That's a parallel line symbol. Alright, so in the next one, which we're calling 24, we've got a new name for this. The linear pairs that are congruent are perpendicular theorem. This one technically came to us as 3-4-1, but hopefully given this name, you can kind of see that we're talking about linear pairs, so a line that intersects another line, and the two angles. And so we know that if you have congruent linear pairs, the value is 90 degrees or perpendicular. And so kind of going off of that first idea, if we have this piece, then our second piece actually tells us that those two meeting points are not only the same, but they are both 90 degrees. Alright. Alright, and then the last one came to us as 3-4-3 in the notes. And it's the perpendicular transversals lead to parallels. So if two coplanar lines are perpendicular to the same line, then they must be parallel. So two lines are perpendicular to another line, they are parallel. And so in that case, kind of again going off of that idea, we've got two lines and a transversal. And so we say they're perpendicular here. And so because of that, we can go to the second phase, which says that same setup is also going to lead to parallel lines. Alright, so those were the three that came up in 3.4.2, and now that we've reviewed them, we're going to move on to the assignment. So here's our 3.4 assignment. We're going to name the shortest segment from E to AD. So remembering in our notes we said that a distance is actually, actually in our parallel lines postulate, the distance between a point and a line is the least at 90 degrees. So here's our point E, here's our line, and the distance that is shortest is going to be at 90 degrees. So EB is shortest. Alright, moving on to the next one, I want you to complete the two-column proof. So we are given that angle ABC and CBE are congruent. So I'm going to write that in here, ABC and CBE. And hopefully that image that I just drew looks very much like one that we just drew here in number 24 from your reasons packet. Notice I'm drawing these two same angle pieces, so we're probably going to end up using, or actually in this case proving, the linear pairs that are congruent are perpendicular theorem. Alright, so they're also telling us that DE is perpendicular to AF, so DE, that vertical line, is perpendicular to AF, which is given by that box. Perfect. So in the first one here, we are told that ABC is congruent to CBE. And you'll notice that as we look in here, the second piece isn't in there. So the first thing I'm going to do is actually fill in the second piece. Notice the given is a little bit further down, and that's just because of the way that the book likes to only use the given once they're, only mention the given once they're actually using it. So that one is an easy piece. Then we're saying that CB is perpendicular to AF. So let's see, CB is perpendicular to AF. And that is what we were just looking at, which was the linear pairs that are congruent are perpendicular theorem. Potentially you can just be talking about linear pairs, but I just want to make sure that we know that it was from that specific theorem. Then we're given that DE and AF are perpendicular, and so because we've just said that these are perpendicular, and we've also said that these are perpendicular, we can now say that they are parallel, those two lines are parallel, by that other theorem, which is perpendicular transversals lead to parallels in purple here. And again, most likely if you abbreviate that or just use the numbers, which we don't tend to do just because that is not really linking the idea, you can just write perpendicular transversals if you would like. Alright, so that was the first proof, kind of using both of those pieces. The next one here, they want you to complete the two-column proof, given that AB is perpendicular to BC, which it is with that red box there. And then 1 and 2 are 180. And so hopefully you can kind of see that 1 and 2 very much look like same side interior angles if we were to say that AAB and DC are parallel. So we are going to prove that BC is perpendicular to CD. So BC is on the bottom there and CD is on the right. So we're trying to get to this piece here where this is 90 degrees. So the first thing is to identify all of our givens, and so they wrote the first piece of perpendicular, but then didn't write that the second piece was given as well, that 1 and 2 are adding to 180. And then by the definition of something being supplementary, we do know that you can say that they are supplementary. Then notice that I mentioned same side interior, and now they're saying converse of the same side interior. And so remember that the converse leads to parallel lines. So we would have just said same side interior, but either way, parallel lines. So now we can say that those two purple lines that I mentioned at the beginning, AB and DC, are parallel. And then because those two are parallel and one of the lines is perpendicular to one of those parallel lines, then that other one is going to be perpendicular as well. And that's going to be our theorem here. That says if we have this setup, which we just drew here, then we can lead to this setup where we have another perpendicular. So perpendicular transversal theorem. Alright, so moving on. We're going to determine if there's enough information given in the diagram to prove each statement. So let's see. First of all, looking at the diagram, if I have something perpendicular to two lines, so this is this one transversal that is perpendicular to these two, those two are going to be parallel because of the fact that those two are perpendicular. And then let's see, I'm just trying to see if we can actually identify if that last line, even though it looks parallel, we need to identify for sure that it is in fact parallel. And so let's see. No, the only thing we can get after that is that, this is 90, and in fact all of these are 90 as well. So that's one of those things in geometry where as much as you think that this looks like it's 90 degrees, unless there's a way that we can actually state that it is 90 degrees, it's not going to be. So let's see. First thing that we note is that 1 and 2 are the same, and they are the same because of vertical angles. So we don't necessarily need the diagram to say. I'm just trying to see if they need us to tell us it is enough information. So we're going to say yes by vertical angles. Then in the next one, 1 and 3, so this is where we need to be careful because anything that's going to take a value from here and move it to one of these angles over here is probably not going to be the same because we do not have parallel lines in that that meet up with that first line. So 1 and 3, we're going to have to say no. As much as you want to say that those are alternate interior, they are not because we are not sure that these two lines are parallel anyway. So then 2 and 3, again, as much as you want to say corresponding, we have to say no. 2 to 4, we have to say no as well. There's nothing that can link those two together. 3 and 4, however, are corresponding, and so we can say that yes, those are in fact the same because of the parallel green marks there. And then 3 and 5 are alternate exterior. Alright. So our last piece here is some critical thinking. Are the reflexive, symmetric, and transitive properties true for perpendicular lines? And we need to explain why or why not. So what we're saying is if we have line L, super, is it perpendicular to line L? Well, no, it can't be perpendicular to itself because it would have to meet it at 90 degrees. So no, and we're going to say this image down here. Alright, symmetric, so the symmetric property says that if L and M are perpendicular, that you can then flip it around and say M is perpendicular to L, and that's a yes. The transitive property says, okay, so we need some more colors here. If L is perpendicular to M, and M is perpendicular to a new line, which is N, then we can just take L and N and make them perpendicular. But L and N end up actually being parallel. So this one's going to be a no as well. All right. So that was our assignment, and then also filling in the reasons packets. We have that as a reference to what it is that we can use during a proof.